This video is on chapter 21.3, Faraday's Law. We will definitely do several examples about Faraday's Law, but I think it would be important to watch both lecture videos on chapter 21.3 and 21.4 before watching any of the demos or doing any of the examples, because really 21.3 and 21.4 go together. They're about Faraday and Lenz's law. So we're starting with Faraday's law, which is all about an induced voltage. So Faraday's law is all about induced EMF. And if you recall from long ago in lecture, we discussed that EMF stood for electromotive force. And really this, for us especially, just means potential difference. And so really what Faraday's law is all about is that for any conductor that experiences a change in magnetic flux, will have an induced voltage across it due to the changing magnetic flux. And so that's Faraday's law kind of in English. What we really need to look at is the mathematical definition. So we'll say, of course, mathematically. And mathematically, we write our voltage symbol a little differently than you're used to. We'll discuss why a little later, but for now you're going to have to take my word for it that the induced EMF, and we're going to put induced down here, is equal to negative d phi sub b dt. Now you might note to yourself that this is the instantaneous and we never work with this. This is calculus. So really it's using the time derivative of the magnetic flux in some area. But what we need to do is write the equation we use, which is the average induced voltage, and that's given by negative delta phi over delta t. So we're looking at the average induced voltage, or it's often referred to as the average induced EMF. We could also note that phi b is, of course, magnetic flux, and delta t is the time for which phi is changing. And so that is Faraday's law. We'll play around a little on the next slide. So we'll say let's play around a little. And so we have the induced voltage. The average induced voltage is always equal to negative delta phi b over delta t. And now we might note here that this negative sign, this is something called Lenz's law, and we will discuss that in the next video. So discussed in 21.4. we might note that your book gives Faraday's law as an absolute value, so it gives it equal to delta phi over delta t in absolute values, because it separates its discussion of the negative sign for the next section. So we're going to put it all together, don't worry. So anyway, the playing around comes from opening up this expression for magnetic flux because it can change in various ways. And so we're going to show you that. So the average induced voltage is equal to, and we'll say delta, but now we're going to open up phi, so we know that's always B, A, cosine lowercase phi, delta t. We might note, of course, that came from phi b equaling that. And we could say C 21.2 if you're confused. And now part of our later thought process will be to decide which one of these factors is changing. And so this can be written several ways. So we could note for changing B, we know that the average induced voltage would be delta B times A cos phi over delta t. And so we could write that delta in front of any of these. So for changing A, and finally for, of course, a changing angle or a rotating loop. And we would have delta cosine phi. And remember, delta is always final minus initial, so this could be written as negative BA cosine phi final minus cosine phi initial, like that. So there you go. That's some useful mathematical expansions on the Faraday law expression. And so I'm going to just add in a bit of an example. And this is kind of an example that we've seen part of before. This is an example where we will determine the induced voltage across, so we'll say this, determine the induced EMF across the 3 centimeter wide ring discussed in the previous example. And this was a 21.2 example. And so we'll be given that the ring is dropped so that it is completely immersed in the magnetic field in 0.015 second. And I'm going to say as shown again, because my examples always rely on some sort of picture. So we have the ring drop so that it is completely immersed in the magnetic field in 0.015 second as shown. And we were asked to determine the induced, we should say determine the average induced EMF across the 3 centimeter wide ring. And that would have to be while it's entering the field, because in order to induce an EMF, it has to be in a changing magnetic field, or the area of the ring has to have a changing magnetic flux. So as we're promised, we need to draw a picture. And it's going to look very familiar. We'll have our ring being dropped downward into a uniform magnetic field. And so those B field lines are directed into the page. And our loop is being dropped downward through them. And so what we're given is that it takes the loop this amount of time to be completely immersed in that B field. So my loop shrank a little, ignore that. This is the instant that the B field is completely immersed in, or that the ring is completely immersed in the B field. And now think about this. If you're this ring and you're falling, you have no B field lines in your area until you start to enter this field. As you fall into the field, you can imagine more and more of these X's would be going through the area of the loop. And it won't be until the loop is completely inside the X's that the B field will then be constant until it starts to leave the field again. And so what we need to do is figure out the average induced voltage, or EMF, across this ring as its magnetic flux changes, as it enters into the field. So, we know that the induced voltage, or the induced EMF average, is equal to negative delta phi B over delta T. And we're just going to ignore this negative sign, really, because we're going to talk more about what it tells... No, we won't. We'll just leave it. We'll talk more about what it tells us later, though. So the induced voltage is equal to, and we have delta B A cos phi over delta T. And so if we think about what's changing here, really, we have... the instant that this starts to enter the field, it has 0 area with B field lines through it. And as it enters the field, more and more of that area are entering the field. And so we could basically say that our final minus initial should be applied, our delta should be applied to A. So we have the average induced voltage equal to B cos phi delta A over delta T. That should be a negative sign. Now, what is the angle between the normal vector to this area? We could represent it as perhaps an X, and the direction of the magnetic field. That angle would be what we put for phi, but as you can see, the magnetic field and the normal are parallel, so cosine of 0 is 1, and we're left with negative B delta A over delta T. Now we can open up this change in area. So we have negative B A final minus A initial over delta T, and our initial area in the B field is just 0, isn't it? And so we can answer the problem. Average is negative B A final over delta T, which is equal to, and we, I think the B field from the previous example that we did was 0.381 Tesla. And the area is pi times 0.015 centimeters, 0.015 meter squared. So I'll write this down there. So A average is works out kind of nice. So we will end up with the average induced voltage, and it will just be the 0.381 times pi times 0.015. And so our induced voltage is equal to 0.017. I guess it would be 80. And that would be Webers per second, or you could just say volts. And so there you have it. So that's an example of Faraday's law and the theory behind it. I have to stop the video now, it's too long.